So in our last class, we have covered topics like contribution of moment about uh, wing and wing body combination, that is the fuselage combination. So we've finished moment about the wing, moment about the fuselage, and the next main thing is the moment about the fuselage, sorry, tail section, because all three things will be a part of the moment about the total plane. That we will see the pitching moment about the complete airplane. So here we need to cover the topics like moment about the tail session and the contribution of moment about the tail, and what are the effects happened because of the aerodynamic interference of flow over the tail, and what are the change in moments because of this aerodynamic interference that we will see in this session. So before going, yesterday itself we finished one or two about the moment about the wing and fuselage. Here we have a problem like a statically stable trimmed aircraft experience a gust and angle of attack reduces momentarily. So a statically stable trimmed aircraft, that means the aircraft is in equilibrium, experiences a gust. So it experiences a gust and angle of attack reduces momentarily. So angle of attack is not increasing. As a result, the center of pressure of the aircraft is A option shift forward, B shift rearward, C does not shift, D coincide with the neutral point. So didn't cover the neutral point and all that we will see in today's session only. But I will tell the answers for this and what is the explanation for this. So here we have three things. When the consider this is an airplane. So consider this is an airplane. So when the airplane is in that means in trimmed position, the lift, this is the lift force acting. The CG and the center of pressure, it remains the same. The CG, when the angle of attack is zero, and the angle of attack is zero, or when the angle of attack, the trimmed angle of attack or alpha E is zero, that means the aircraft in steady level flight. Then CG is equal to CP, that is the center of pressure is equal to the CG. So when the angle of attack increases, that means aircraft is pitched up. Yesterday itself we have seen that when the angle of attack is increasing, that is alpha A greater than alpha E, means the aircraft is pitching up. So aircraft pitch up. When the angle of attack is decreasing, that is alpha A less than alpha E, then the aircraft pitch down. Okay, just remember this. When the angle of attack is decreasing, aircraft pitch down. When the angle of attack is increasing, the aircraft pitch up. So here the aircraft is pitching, so pitching down. So as I told earlier, suppose the aircraft is if an aircraft increased aircraft experience a gust, the moment will act on the airplane, and the moment if the moment is acting, automatically what will happen? Here what is happening means the center of pressure, here it is a CG. They are asking about the experience of center of pressure. Here also it is a CG. What is happening? This center of pressure, it will shift forward for pitching down moment, and center of pressure here it will pitch backward for pitch up moment. So for pitch up, the center of pressure will move backward. For pitch down, the center of pressure will shift forward. Also we can say like this: when the angle of attack increasing, the center of pressure moves backward or shift rearward. When the angle of attack is decreasing, the center of pressure shift forward. Therefore, here the answer is the A, that is the center of pressure shift forward. So this is the answer for this, the center of pressure effect here. Do you know what is center of pressure? Center of pressure is the point at which the net moment uh, due to the pressure distribution is zero. That means the moment will be zero. The moment because of the pressure distribution will be zero. That's why the point. So we know the pressure distributed all over the surface of the airfoil and the airplane. Center of pressure is the point at which the net moment because of the pressure distribution is equal to zero. The net moment will be equal to zero. The moment is due to the pressure distributed over the surface of the aerofoil or the whole plane. Okay. So the next thing is the next problem. The primary function of so for this problem we don't want to see the contribution of tail and all because we already know the effect of fin in the vertical tail of an aircraft. The primary function of the fin in the vertical tail of an aircraft is to provide yaw control, yaw stability, roll damping, roll stability. So we know the vertical tail and the fin is used for the stabilizing the aircraft. So the main function of the vertical tail is to for yaw stability. Rudder is for elevator is for pitch stability. So here and the aileron is for roll stability. Therefore, the answer is yaw stability. Here we have the answer is B, yaw stability. So the aircraft, the primary function of the vertical fin in the vertical tail is tail of the aircraft is to provide yaw stability. Vertical this tail is all mainly used for the stability of the aircraft. So the vertical tail is for yaw stability. Okay. So the answer is yaw stability. So next thing is a contribution of tail to the moment about the center of gravity. So here we have that we already know our study itself. I have explained that if an pitching moment across, that means if an aircraft experience a gust or some load or that means if it moves down or when the angle of attack decreasing, the aircraft pitches down. So a pitch down movement acts on the airplane, and what we need to do is if it is a statically stable aircraft, a opposite movement or a clockwise movement should occur on the particular airplane to produce the restoring force or to bring the airfoil or aircraft back to the equilibrium position. Suppose an anti-clockwise moment acts on the airplane means the aircraft cannot be bring back to the equilibrium position. So for that purpose, we are using a tail. So because of this tail, what will happen means the aircraft will aircraft is brought back to the equilibrium position. In the tail, opposite or negative lift is acting if for a pitch down movement, and because of that the aircraft is pitched up and brought back to the trimmed position. So this is the purpose of the tail. So here we have uh, two interference effects that influence the tail aerodynamics. One is due to the downwash, the airflow is deflected, and the airflow over the wing, the relative wind over the wing, the direction of relative wind over the wing is not same in the tail aircraft because of the downwash. The relative wind is also deflected because of the downwash, and we have a relative wind in uh, different direction. And the second one is the speed of the relative wind that flows over the that which reaches the wing is not same as the speed of the relative wind that reaches the tail. So there are two effects because we know that because of the aerodynamic effects um, and because of the vortices, trailing edge vortices and all, the airflow over the wing is slow down and it reaches the tail of the aircraft. So the speed which encounters in front of the airfoil, sorry, in front of the wing is uh, slow down, and the speed changes when it reaches the tail. So what we are considering here is the relative wind over the wing is we are considering it as V infinity, and the relative wind over the tail is we are considering it as V dash. This is the difference we are giving, and also the direction. As I told that the flow of the tail is deflected downwards due to the downwash and all. So here also the relative wind is deflected downwards, and it may not be the same direction as it reaches the wing. So here we have the diagram for the wing, and this is the wing part. It is a wing body part. I can write this wing body, and this is the tail part. You can see this here. So there are some notations. So the tail plane, uh, it is at a distance of LT from the center of gravity, and it is at the height of ZT from the center of gravity. So the vertical height is ZT, and horizontal distance is LT. This is the zero lift line. So here we can see the zero lift line for the tail is different. So this is the zero lift line for wing body combination, and here the as I told that for symmetrical airfoil and all, zero lift line is equal to the chord line. So zero lift line is equal to chord line. Chord line. We know the for tail and all we will be using symmetrical airfoils only. So therefore the zero lift line of tail is equal to the chord line of the tail. Zero lift line of tail is equal to the chord line of tail. Note this thing also. And the tail airfoil is a symmetrical airfoil only, and therefore the zero lift line of tail is equal to the chord line of the tail. And here you can see the downwash angle is epsilon, and here we have the tail setting angle IT. That is we are setting the tail at some different angle because the airflow over the wing should not affect the airflow over the tail. So therefore we are keeping the tail at some different angle, and this is the LT, and LT is the lift force acting on the tail, and DT is the drag force acting on the tail. The moment about the aerodynamic center over the tail is MACT. So here we can see uh, the tail is deflected somewhat downwards. So the angle is alpha WB. The lift force is inclined to some angle, that is here it is alpha WB minus, this is so the relative wind is deflected at an angle alpha WB, but here we can see the relative wind V dash is deflected to somewhat uh, by an angle of epsilon, that is a downward angle. Therefore the lift and drag force is deflected at an angle of alpha WB minus epsilon. Same drag is, so therefore the lift force it is splitted into two components, that is LT cos alpha WB minus epsilon, and the same way, and also cos and LT sin alpha WB minus epsilon. This WB and all it is a suffix. So therefore drag is also, it is splitted into two components. One is a vertical component, another one is the uh, horizontal component, that is a dt sin alpha WB minus psi. Same way dt cos alpha WB minus psi. So the sum of moments about the center of gravity are LT, dt and M ACT. So these are the moments acting on the tail of the airplane. So the total moment about the tail is the mcgt equal to LT into, because we are calculating the moment for the center of gravity. So the center of gravity from the tail is LT cos alpha WB minus epsilon into LT plus dt into sin alpha WB minus epsilon into LT, and the minus symbol indicates that it is in a negative direction. So therefore it will be minus, the same way, plus ZT into LT sin alpha WB minus epsilon minus ZT into DT cos alpha WB minus epsilon, plus we have the another not only lift and drag forces acting on the airplane, we have another moment about the aerodynamic center. So MACT plus we are putting like MACT. So there are some assumptions that we are using for conventional airplanes. We know that for conventional airplanes, this vertical distance from the center of gravity is very much less than the horizontal distance. So the vertical distance is neglected, and also the drag of the tail is very much lesser than the lift of the tail, so that part will be neglected. And also already alpha WB is small, but here it is lesser than alpha WB, that is we have a downward angle also, we are subtracting the wing body angle with downward angle. So therefore the angle is very small, hence alpha WB minus epsilon is equal to 0, and but cos alpha WB will be equal to 1. And also one more thing, the moment about the aerodynamic center of the tail, that is MACT, it is also neglected because of the, because it is very small in magnitude. Therefore these four things it get neglected, and it is reduced to, the equation will be reduced to only thing. So this part is neglected, and also this part will be neglected, and drag is also neglected. So the remaining terms will be, we know the cos alpha WB minus T minus epsilon is reduced to 1. So therefore the equation becomes mCG T equal to minus LT into capital LT. minus LT into capital LT. So the equation becomes like this. So now we can we already know CLT equal to, that is CLT equal to the coefficient of lift equal to LT divided by Q infinity S into T. Sorry, S suffix T. So therefore by substituting the value for L here, the equation becomes M Cg of T equal to minus LT Q infinity ST into CLT. Now what I am going to do is I am dividing the term with Q infinity S into C, the equation by Q infinity S into C. Then the equation becomes, we know M divided by M Cg of T divided by Q infinity S C equal to the moment coefficient. It is a formula for moment coefficient. Therefore we can write like this: Cm Cg of T equal to minus LT ST divided by CS into CLT. CLT. So here this part we can say it as it is a volume ratio. There is a volume ratio that is equal to, we are denoting the term as VH, V suffix H, that is V suffix H equal to LT, not the minus symbol, only the term LT ST divided by C into S. That is, it is LT ST is the volume characteristics of the size and location of the tail. So this is the location and size of the tail, and CS is the volume characteristics of the size and sorry, here we are not considering the location, we are considering the chord term, and this is the location of the size of the tail. So all over we will call it as a tail volume ratio. We are denoting the term as VH. Therefore the equation becomes CmCg of T equal to minus VH into CLT, minus VH into CLT. So here the equation gives the total so this equation gives the total contribution of tail moment about the center of gravity. So another one thing, we know that some other factors also which affects the tail, that and all that we will see here. So here this alpha T, that is a tail angle of attack, is equal to alpha WB minus IT. We are including this IT term because the tail is setted at tail setting angle of IT. So here this is the tail and this is a zero lift line, and it is setted at an angle of IT. So therefore the alpha T will be, that is equal to alpha WB minus IT minus, by subtracting the terms of IT and downwash angle, we will get the alpha T. So CLT equal to AT into alpha T, where AT is the slope of the tail, that is a lift curve slope of the tail, and alpha T we can substitute the value here, and also we know the downwash angle, that is a downwash equal to downwash of the tail is equal to downwash of the wing body combination, that is epsilon plus 0 plus dou epsilon divided by dou alpha into alpha WB. So straight away we can put the value of epsilon here. So the equation becomes CLT equal to A into alpha B into 1 minus dou epsilon divided by dou alpha minus AT into IT plus epsilon 0. So I'm substituting the CLT value here. So we can get like this: CMC CG of tail is equal to, there is a moment, question of moment about the center of gravity of the tail is equal to minus AT VH alpha B into 1 minus dou epsilon divided by dou alpha plus AT VH into epsilon naught plus IT. So this is the equation for finding the center of moment question about the center of gravity of the tail. So guys, please note these two formulas. These two formulas. So please intimate me when you finish the formula. So here this CLT term, we are substituting the value in this equation. So after substitution only, we are getting this final equation for center of moment question about the center of gravity of the tail. Okay. Did you guys finished? Anyone please reply? Finish noting down this formula, students. Anyone? Shall I move on to next topic? Guys, okay, fine. So we finished the moment about the center of gravity. Now we need to move on to the topics like equation of stability, static margin, neutral point and all. So next topic is the total pitching moment about the center of gravity. So total pitching moment. That we have now we have see already we have seen the wing body combination and tail plane combination. That means the center of moment question of both the center of gravity of the both parts, but all together is called the moment about the center of gravity. That is the total pitching moment about the center of gravity. So for whole plane, we need to just add the both the terms. That is a moment about the center of gravity of the wing body combination and the moment about the center of gravity of the tail combination. So by substitution, we will get the moment about the center of gravity is equal to, that we have seen here, yeah, CM AC. So this is the moment about the center of gravity of the tail plane and this equation. The same way we have equation for moment about the center of gravity of the wing body combination, that is a MCM AC WB plus alpha WB into uh, AWB into H minus HAC WB. So this equation I'm going to substitute it in the total pitching moment formula. So the equation reduces to CMACWB plus CLWB. So because as I told, CLWB equal to AWB into alpha WB. So for this I am putting like this. For this part I am putting CLWB. So the equation is CLWB into H minus HACWB minus this part is for the tail plane. There is a moment about center of gravity of the tail is equal to VH into CLT. Now I am substituting the whole values. This equation. Moment about center of gravity of the tail is equal to minus AH VH into alpha B. So the equation become CMACWB plus AWB alpha WB into H minus HACWB minus VH into AT divided by AWB, because I am taking the whole term as a common, into 1 minus dou epsilon divided by dou alpha plus VH AT IT plus epsilon naught. Here I have this AWB is equal to, assuming that AWB is equal to A for the whole plane, and also CLWB is equal to CL for the CLWB is equal to CL for the complete airplane. So therefore the equation be reduced to CM ACWB plus A into alpha A into H minus HACWB minus VH into AT divided by A 1 minus dou epsilon divided by dou alpha plus VH AT into 1 minus epsilon naught. So this is the pitching moment coefficient formula for the whole airplane. So if they are asking to find the pitching moment formula for the whole airplane, just note down this formula, so that you use this formula and find the answers. Here VH is the tail volume ratio, and volume ratio, the tail volume ratio of the tail volume ratio tail. This is the momentum of wing. So this is slope, lift curve slope, for whole plane, lift curve slope. And this is the lift curve slope for tail plane, curve slope of tail. This is a downwash angle for whole plane, or sorry, for wing body combination, for wing body. This is tail setting angle, tail setting angle. So they will give the values for all these things, and they ask us to find the answer for moment about the center of gravity. If they are asking like that, means you need to substitute the formula and find the answer for this whole thing. Okay. This sum and all we can solve somewhat later. We will finish the theory parts and we can solve the sum. Okay. So next thing is the equation for longitudinal static stability. So as I told earlier that we have discussed earlier that for longitudinal static stability, Cm0 must be positive and dou CmCg divided by dou alpha must be negative. So the equation for giving that static stability is moment about center of gravity, that is Cm0 is at zero lift condition is called Cm0. So Cm0, or we can write like this also, CmCg at L equal to 0. That means moment about the center of gravity only when the lift is 0. Then the condition is called Cm0. That is equal to CmAC WB plus VH into AT into 1 IT plus epsilon naught. That is Cm0 must be positive to balance. For in order to balance the airplane, Cm0 must be positive. And one more thing, they will ask questions like this. They will give some initial values that for or some given data to find the whether the aircraft is in stable manner and also balanced manner. So for in order to balance the airplane, we need Cm0 must be positive, and also to stabilize the airplane and all for stability and also for balance, this both conditions should meet. So first you need to find this condition whether the Cm0 value is positive. So we need to substitute the value for suppose they are giving value for downwash angle for wing body combination, tail setting angle, and also lift curve slope for tail, and also the volume ratio, and this value also. If they are giving this values and you are getting answer for Cm0 as negative means, as negative value means, straight away you can say the aircraft is not in balanced position, the aircraft is not balanced. But if this value is positive, because you are getting value like the positive 0.01 means it is positive. Suppose it is positive means the aircraft is balanced. So they will ask conditions like, they will give some data, they ask us to find the values, and they ask only whether the aircraft is stable or not. You need to find the answers, and after with the answers only you need to conclude that the aircraft is in a stable position or in a balanced position. The next is the dou CmCg value by dou alpha. So same thing here also. uh, you need to find the value for these things, and with the answer you need to conclude whether the aircraft is statically stable or not. Cm0 for balancing the airplane. Here it is for whether the aircraft is longitudinally statically stabilized or not. We need to find the answers and conclude with the values. The next thing is the neutral point. So for neutral point, so at some condition, dou CmCg by dou CmCg divided by dou alpha A value will become 0. For some condition, the slope will be 0. The point where, or the location where the center of gravity about the that is CmCg by dou alpha is 0 is called, that point is called a neutral point. So the point where the moment coefficients will be 0 is called the neutral point. So in aircraft also we have a neutral point. This a neutral point is mainly used for the stability of the airplane. So here we have the formula, that is dou CmCg by dou alpha naught. If it is becomes 0, the equation becomes 0 equal to A into H minus HACWB minus VH into AT divided by A 1 minus dou epsilon by dou alpha. that only I am mentioned here. I'm putting the value of dou CMCG by dou alpha is equal to 0. By putting the value, we can have like this. And when when this dou CM by dou CMCG by dou alpha is A equal to 0, we can hold the conditions for neutral point. So the H will be, we can denote the H as Hn. So Hn equal to, we can write like this by cross multiplication, A will be become 0. So therefore the equation becomes Hn minus HAC WB minus VH into AT divided by A 1 minus dou psi by dou alpha is equal to 0. So from that Hn equal to HAC WB plus VH into AT by A 1 minus dou epsilon divided by dou alpha. So this is the equation for neutral point. So suppose they are asking us to find the location of the neutral point, means you need to use this equation to find the neutral point of the airplane. So this is the main condition for a longitudinally statically stable. So for a statically stable aircraft, the position of center of gravity must be, that means the CG must be, suppose we are having neutral point here, means this is a neutral point. Simply I am saying here it is the CG of the airplane. In order to have the aircraft longitudinally statically stable, we need the CG should be forward of the neutral point, or far ahead of the should be ahead of the neutral point. Then the aircraft will be statically stable. So here we have the conditions like when the CMCG will become 0, H is equal to Hn. So here three curves are there. One is that the H is equal to Hn, and one is H greater than Hn, and another one is H less than Hn. So next is the static margin. So here we can see this neutral point and the center of gravity. The distance from center of gravity and neutral point is called the static margin. We know this from the leading edge. We are considering the distance from the leading edge to the center of gravity is called H, and the distance from leading edge to the neutral point is called the Hn. The distance from leading edge to neutral point will be considered as Hn, and the distance from leading edge to the center of gravity is considered as H. That means in chords, distance in chords. So that's why they are given us CH here, CHN. If the chord is 1, it will be reduced to H. So that's why. So in between this distance from CG to the neutral plane will be called static margin. That is Hn minus H, Hn minus H. This Hn minus H is called static margin. So for this equations, dou CMCG by dou alpha A equal to A into H minus Hn. So here we know the Hn minus H equal to is called the static margin. So taking the negative sign outside, we will get like this, or interchanging, we will get minus A into Hn minus H, that is equal to minus A into static margin. Note this formula. From this formula, so many problems are asked. So just note this formula. So this static margin, so we should know what is the static margin and why we are using. So as I told that for statical stability, the neutral point should be in a rearward to the center of gravity, or the center of gravity should be far ahead, or it should be ahead of the neutral point. So for a statically stable aircraft, the static margin, so this distance should be positive. If this distance is positive, we will get more stability, and if the distance is negative, means it is unbalanced. That means when the neutral point it shifts before CG, means the aircraft is in unbalanced condition, that is a unbalanced static stability, uh, or we can say it as a statically unstable aircraft. If it is in the backside, the aircraft is statically stable. So for the here the condition is for statical stability, the static margin should be positive. Larger static stability, the more stable the airplane. If you have larger static margin, that means the more positive values we will get, the airplane will be more stable. The next topic is stick fixed longitudinal static stability. Stick fixed longitudinal static stability. We have two conditions. One is a stick fixed condition, and another one is a stick free condition. So in older aircraft and all, we are having the stick fixed conditions because yeah, so many problems are encountered for this while flying an aircraft with the stick fixed condition. That means in olden day aircrafts, that means World War aircrafts and all. What we need to do is they were having they are good in maneuvers, but while in critical conditions and all, what they need to do is the pilot only he will pull or push the control stick and hold the control stick rigidly to or do maneuvers and all, for doing maneuvers and all. While doing such type of maneuvers, what happens? The pilot need more effort to hold the stick here. So for reducing that and all, only now hydraulic controls are used. Hydraulic stick controls are used. So in older days and all, there is no way for that type of controls. The pilot only should hold the airplane in such manner by using the control stick. So he moves the control stick, and he should hold there for doing such maneuvers. So in other yeah, as I told earlier that we have conditions like for statically unstable aircraft, we need to deflect the elevator for bringing the aircraft back to the equilibrium position or trimmed position, or in a condition for a statically stable aircraft. So for such conditions and all, what the pilot need extra need to give extra force to hold the uh, elevator in such deflected positions. Then only the aircraft will get back to the original position. So this type of condition is called stick fixed statical stability. But it is in some conditions and all, the pilot doesn't have such force to hold the elevator or hold the control stick in some given positions and all, or some in a rigid manner in a to a fixed position. So because of that, some problems encountered during flying. So in order to minimize that, only hydraulic type control sticks are used, so that yeah, we don't the pilot won't feel the pressure while moving the control sticks and all. But in olden days, pilot will feel the pressure to deflect the control surfaces. That's all. So this is called stick fixed stability. So already we know that the elevators and all, it is fixed to the tailplane by using some hinge movements. Nowadays, so many other techniques are there. Morphing type tails are there. There is a passive morphing, active morphing tails are also there. But normally we will use hinge type elevators. So this hinge type elevators also, it will also give some moments. So that type of the moment created by this elevator hinge is called elevator hinge moment. We are giving the formula for elevator hinges CH equal to HE divided by half rho infinity V infinity square SC into CE. Same that so here so consider this is a tail of the aircraft, and in the tail plane, suppose this is the elevator. It is hinged here by a hinge point. So when it is when the hinge angle, that is del E is 0, the pressure distributions will be equal. So there won't be any lift acting here. The pressure distribution over the surface of the elevator and the bottom the surface of the elevator is same. So there won't be any lift. When it is deflected downwards, the del E changes. That is a elevator angle, uh, trim angle changes. So there is a variation. If it is deflected downwards, the top surface will give less pressure, and the bottom surface, more pressure acts on the bottom surface of the elevator, and because of this, lift acts on the tail plane of the or elevator of the airplane, and totally the tail will be deflected upward and to balance the airplane. So this is a hitch movement. So this is a moment acts on the elevator of the airplane. Next is the stick-free static stability. So this for elevator, we have a formula for elevator trim. Some problems are asked regarding that also. There is a elevator del trim. What is del trim means? Suppose the elevator is deflected to some angle. We need to trim the this much angle to bring back the elevator to neutral positions and all. So that is called the elevator angle, trim angle. So the formula for elevator trim angle is del trim equal to Cm naught plus dou Cm Cg divided by dou alpha A into alpha A divided by Vh into dou CLT, this is CLT divided by dou del E. Just note down this formula. This formula is also needed. Just note this formula. Intimate me when you finish this noting down this formula. Have you finished noting down this formula? Anyone please reply? Shall I move on to the next topic? So one more thing here. If the elevator hinge is elevator is deflected downwards, this Delhi angle will be positive. It is positive. When the elevator is deflected upward like this, the elevator angle is negative. The elevator angle will be negative. And also one more thing. So we know we are calculating the moment only. So when elevator angle is 0, the elevator deflection moment will be like this. So the CM0 will be here, and we have the trim angle of attack here. So when the elevator will be deflected, see here it is deflected at a positive some value. If it is deflected to some positive angle, the CM value also it will move towards some new value. That is, we will be having a new moment. Some moment is also changing. So for that we will be getting a new trim angle. There is a new trim angle of attack here for this, and the delta is also changed. The deflection, when the deflection is changing, automatically the trim angle is also changing, and the moment is also changing here. Okay. So next thing is the stick free longitudinal static stability. So if the elevator is allowed to float free because of the influence of the natural aerodynamic forces and moments of the tail, then that type of stability is called stick free static stability. So there are two types of stability. One is stick fixed static stability. That means the stick is fixed at some position to stable the aircraft. Another one type is the stick free static stability. In the stick free static stability, the elevator is allowed to float free so that it can move free, and it will move to some position. Uh, uh, so initially the elevator is fixed somewhat, it will be at some position. That at that position is called the at that position the hinge is equal to 0. Hinge moment is equal to 0. After that it will float. When the aircraft is pitching up, it will also float to some another position, and the angle at that position will be called the del free angle. That is in the last session, previous topic, we have seen about del E, or here the del E is changed to del free because the elevator is allowed free to float here and there. So when the aircraft is pitched to some position, what will happen is the hinge the elevators is also it is moved to some position. At that time the angle is called del free, and it automatically balance the airplane by in a statically stable condition. So here we are considering the elevator equilibrium deflection angle for a free elevator. That is a this is the formula. That is a CH equal to, as I told that it is float free. Therefore the hinge is equal to 0, moment equal, 0. Therefore H equal to 0. Therefore this moment it will become 0. But the formula is CH equal to dou CH divided by dou alpha t into alpha t plus dou H divided by dou del E into del free. So for normal elevator hinge, the formula will be CH equal to dou CH divided by dou alpha t into alpha t plus dou CH divided by dou del E into del E. Here this del E is changed to del free. Therefore here I am writing like del free, and this, as I told, for stick free force H will be 0. Therefore this moment will be equal to 0. That means there was we don't have any force to deflect the elevator. That's why H will be equal to 0. So therefore CH will be equal to 0. Then the equation becomes, we can calculate the del free value from this equation. So therefore del free equal to minus dou CH divided by dou alpha t divided by dou CH divided by dou del E into alpha t. We know from the previous equation we found the CLT value. So the CLT value equal to, CLT formula is equal to alpha t AT alpha t plus CLT divided by dou del E into del free. So here substituting the value for del free in this equation, so this value in this equation, we will get CLT equal to AT alpha t minus dou CLT divided by dou del E into dou CH divided by dou alpha t divided by dou CH divided by dou del E into alpha t. So here this equation, it is reduced to AT alpha t into F. So this term I am putting the value of this term as F. So F is the free elevator factor. F is the free elevator factor. We don't need this derivations and all. We need this equation for, and this equation also, because in one sum they have given values for AT, this value, this partial derivative value, and these two partial derivative values. And they ask us to find the value for this free elevator factor. And one more thing, this free elevator factor is, it is always less than 1 or less than unity. So it is of the order of 0.7 to 0.8. So while solving the problems also, the answer should be within this limit only. So think while just note down these values, because it should be less than unity. It should be less than unity. The free elevator factor is should be less than unity. Okay. So for a fixed elevator moment, the moment coefficient is equal to CMCG equal to CMACWB, because we have some derivations here. We can neglect the derivations and note the final formulas only. Here this is the formula for moment about the center of gravity. The CMCG equal to CMACWB plus CLWB into H minus HACWB minus VH into CL of T. That is for a dash, we represent it for a free condition. That is without the C dash MCG means it is for stick free condition. This is for stick fixed condition. So we can substitute the value for CLT. We have seen earlier that CLT equal to AT alpha t into F. By substituting here, the equation becomes CMCG equal to CMACWB plus CLWB into H minus HACWB minus VH into AT alpha t into F. Okay. So these are the other formulas for solving. So dou CMCG by dou alpha equal to minus A into Hn dash minus H. For stick free condition, the Hn will be changed to Hn dash. Same way, we already calculated the Hn value. So here I'm putting H dash, and the value will be Hn dash equal to Hn HACWB plus F into VH into AT divided by A 1 minus dou epsilon divided by dou alpha. The same way, moment about center of gravity at zero lift coefficient for stick free condition is C dash M0 equal to C dash CM WB plus F VH AT into I T plus epsilon. Okay. So next thing is the directional stability. We are not going deep into directional stability and lateral stability now. That we will see later. Now we can see what is directional stability. So in longitudinal stability is about lateral axis. We know the longitudinal stability is about lateral axis, and lateral stability is about longitudinal axis, and directional stability is about a normal axis. So in longitudinal stability, because it is about lateral axis, only pitching moment occurs. So when the aircraft pitches up and down, the aircraft should automatically corrected to its original position. Then the aircraft will be called as statically stable aircraft. For lateral stability, it is about longitudinal axis. So the aircraft will roll to the port side or roll to the starboard side. So when it rolls to the port side, the aircraft should correct to its original position, or when it is a roll and yeah, combined combination will happen. So that we will see later. For the instabilities happened in directional and lateral instability, we will see later. So here for directional static stability, it is about normal axis. So the moment happened in directional static stability is the yawing moment. So this yawing moment is about the z axis. So here we have three diagrams, three airplanes. In the first one, there is no yaw is happening, so the aircraft is directionally stable. And in the second one, the aircraft is yawed to right. So what is happening means, this in the tail, perpendicular force is acting. The force is perpendicular to the relative wind velocity, that is v infinity, and because of this perpendicular force, the tail portion is shifted to its equilibrium position, or trimmed to its equilibrium position, that is this red line, and the aircraft is bring back to the uh, neutral or equilibrium position. This is called directional stability. In the same way, if the so the moment acting here is, when it is yaw to the right, a anti-clockwise moment acts on the airplane, and when it is yaw to the left, a clockwise moment acts on the airplane. So when it is yawing to the right, anti-clockwise moment acts on the airplane. When it yaw to the left, clockwise moment acts on the airplane to bring the aircraft back to the position. So here we have a formula for vertical tail volume ratio, and we can see uh, how much vertical tail should be there. The volume ratio we can calculate here. So here we have the aerodynamic center of the tail. It is at a distance of LVT from the center of gravity. This is the CG, and we have the area of the area of the vertical tail is considered as SVT. So the tail volume ratio V suffix Vt equal to, it is equal to the LVT SVT divided by B into S. So LVT, it is the distance of the vertical tail from the center of gravity. SVT is the area of the tail at the area of the vertical tail around. And BS is the area and span of the wing. Okay. So vertical tail volume ratio uh, VVT equal to LVT into SVT divided by B into S. Okay. So next is the lateral stability. So lateral stability is about longitudinal axis. So the aircraft will roll or roll, and because of the roll, we know, or we can say the aircraft banks to the port side or banks to the starboard side. So there will be a banging angle. So when the aircraft banks, the bank angle increases, and the opposite moment should act on the airplane to correct the bank angle, or to trim the bank angle, so that the aircraft will be in equilibrium position. So here also the main problem in lateral stability is the side slip, or here the side slip is the sideways motion of the airplane. So it is called the side slip, and there will be a side slip velocity, that is Vs. So how the side slip occurs, we will see here. So consider here we can see, uh, that's why we are considering dihedral wing for to minimize this side slip and all. So for a dihedral wing, the wing will be like this. It is tilted to some angle, that is called the dihedral angle, gamma. So here we have this low wing configuration of airplane. So when the aircraft is banking, what will happen? The lift will be acting like this, the weight is acting like this, and um, as we are banging the airplane, the bang angle increases. The bang angle here, we are considering the bang angle as phi. It is increased like this, and consider we know the both in both planes lift will be acting. Lift is produced on both sides of the plane. So while during banging, this lift will be same. So because of this lift, what will happen? The aircraft will be um, moved somewhat away from the away from the plane of symmetry. This movement is called side wash, because uh, both sides are left is equal, and because of that, what will happen? A side wash angle is motion will be produced over the airplane. But for this is for low wing aircraft, low wing, no straight wing aircraft. But if you are giving a dihedral wing like this, what will happen means the lift on both sides will not be same. If the lift on both sides will be is equal, then side slip will be produced, because slight slip velocity is induced, and this moves the airplane to some new position, and aircraft will be slided down from the equilibrium position. So this problem is called the side slip problem. So in dihedral wing, the lift may not be equal in the both wings. That means the lift in the left wing and the right wing is not equal, and because of that, the aircraft is corrected to its original position. See here, lift on one wing is more, and lift on other wing is lesser. So this causes the airplane to uh, moment to so that if it is a roll towards left means an opposite moment will be acting, and this opposite moment corrects the airplane. But here we can see the moment is also like this, and this causes the airplane to skid from the original position. So that's why we are using dihedral wing for this stability. This type of stability is called lateral stability. So here in lateral stability, the rolling moment is restored, and the aircraft is brought back to the original position by using by the design of the wing, that is the dihedral type wing. So now we can see the problems. So this all for the stability is lateral, longitudinal, and directional stability, and we have some instabilities also. That is angle of spin, Dutch roll. These things and all we will discuss later in our next class. We can discuss here these topics. Now we can see the problems regarding this stability criteria. So here we have consider a wing body model. So we are considering a wing body. So the formula should be also in a WB with CM ACWB. So moment about the aerodynamic center of wing body combination is minus 0.032. That is then A is equal to the lift curve slope is equal to 0.08. Then alpha A equal to alpha A, we know the formulas have A and alpha A. So the alpha equal to 9.38. Suppose they will also give the geometrical angle, because alpha A equal to geometric angle alpha plus alpha L equal to 0. That is a geometrical angle plus 0 lift angle of attack. They will give both the values, and both the values means you should substitute the value first in this formula and find the value for alpha A, and after that you substitute the values in your equation. Okay, don't take this two values and substitute okay, first we need to find the value for alpha A, and after that only we should find the we should substitute the values in the main equation. Then H minus HAC WB equal to 0. So the momentum is equal to 0.11. The area and chord of the wing are 0.1 meter square and 0.1 meter. So the area is 0.1 meter square, chord is 0.1 meter. Now assume that a horizontal tail is added to this model. Assume that a horizontal tail is added to this model. The distance from the airplane center of gravity to the tail aerodynamic center is 0.17 meter. The tail area is 0.02 0.02 meter square. So the um, tail setting angle, so they have given the tail setting angle I suffix t equal to 2.7 degree. The tail slope lift slope is 0.1 per degree, and from experimental measurement downwash angle is 0 for the wing body. Then dou epsilon by dou alpha is equal to 0.35. If alpha equal to 7.88 degree, calculate the moment about the center of gravity for the airplane model. So we need to calculate the moment about the center of gravity for the airplane model. Whether you can able to solve the sum? Anyone? You guys able to solve this sum? Students, anyone please reply. can solve the sum or other I need to solve the sum? Please reply me. I couldn't able to hear you. Guys, please don't write in chat box. Just reply me because I couldn't see the. Otherwise, I need to end the shows and end the PPT. Close the PPT and then only I can see the chat. So please reply me with words. Okay. Uh, so shall I solve the sum? So we have they asked us to find the moment cohesion about the center of gravity. So first we need to know what is the formula for the moment cohesion. So here we have the formula CMCG is equal to CMCG equal to CMACWB plus A alpha A into H minus HACWB minus VH into AT divided by A into 1 minus dou epsilon divided by dou alpha plus VH into AT into IT plus epsilon naught. So I will write the formula here, and after that we can solve. So CMCG equal to CMACWB plus A into alpha A H minus HAC WB minus VH into AT divided by AT divided by A 1 minus dou epsilon divided by dou alpha plus VH into AT IT plus epsilon naught. So note this formula. Here we can see now whether they have given the values for all these things. CMACWB. So in equation they have given the value for sorry, in the question they have given values for CMACWB, that is equal to 0 point minus 0 0.032 plus A, value of A is 0.08. So therefore 0.08 into alpha A, that is into 0.08 into alpha A is 9.38 into H minus HAC. Already they have given values for H minus HAC, that is 0.11 minus VH they haven't given values for VH, but they have given values for area and the chord value, that is 0.1 into 0.1, and also the distance from the center of gravity of the tail aerodynamic center is 0.17 meter, and the tail area also they have given. We know the formula for tail volume ratio, VH equal to VH equal to LT into ST divided by C into S. So LT is the distance from the center of gravity of to the tail aerodynamic center. So therefore, the values are for LT they have given 0.17. So therefore, 0.17 into 0.17 into tail area, that is ST is the tail area, that is equal to 0.02. 0.02 divided by C into S. We know the chord is 0.1 and also area is also 0.1. So therefore 0.1 into 0.1. Please anyone calculate the value and tell me the answer. Calculate the value and tell me the answer.
So 0.34.
0.34. So the answer is 0.34. So you can substitute here 0.34 into then next thing A suffix T divided by A. A suffix T is the lift curve slope. So the tail lift slope they have given values like 1.0.1. So they am substituting as 0.1 divided by A. Sorry, what A only. So A equal to 0.08. So therefore divided by 0.08 into 1 minus they have given value like dou epsilon by dou alpha equal to 0.35. So therefore 0.35 plus same volume ratio 0.34 into A suffix T, that is 0.1 into IT value they have given the tail setting angle is 2.7. So therefore 2.7 plus downwash angle about the wing body configuration that they have given 0. So now calculate the value and tell me the answer for CMCG, moment about the center of gravity. You can easily calculate because all values I have given here. Just calculate the values and tell me the answer. Guys, have you calculated that? Okay, fine. So everyone got the answer like this: 0.065. 0.065. Everyone got the same answer? Anyone? Please reply.
Yes, sir.
Okay, okay, fine, fine, fine. So this is how we need to solve the sum. So just note the formulas. They won't ask this much big this type of sums because sometimes they will ask but they will ask like they will given the values and whether they will ask whether the aircraft is stable or not, that they will ask. Okay, so next thing, next problem, consider the wing body wind tunnel model. So there is a model. Does this model have longitudinal static stability and balance? So we need to find whether the model is model have longitudinal static stability and balance. So for static stability, in order to find the static stability and all, we need to find two things. One is CM0, as this I have told earlier also, CM0 and dou CM CG divided by dou alpha A. Okay, so for finding the stability and all, we need suppose they have asked questions for to find the static stability, and they have given some values, means we just away write the formulas for this both things and find the values for this two formulas, and then with that answer you just conclude that whether the aircraft is in stable condition or not. Okay, so for aircraft should be stable, the value should be cm0 should be positive, and dou cm cg divided by dou alpha should be negative. This should be positive, and this should be negative. Then only the aircraft will be in a stable condition. If opposite happens, means then the aircraft is not stable. Okay, that is, it is statically unstable and not balanced. So shall we find whether you can find the answers? Do you have the formulas for finding so cm0 and dou cmcg divided by dou alpha a? And one more thing, if they are given that wing body tail combination, you should consider the formula for both the wing body and tail combination formula. If they have only given the wing body combination, means just only take the formulas for wing body combination. Okay, so we have seen two types of formulas. One is for without the tail combination, and then one with the tail combination. Okay, we have seen formulas separately for wing body combination and separately for tail combination, and we have also seen formulas for the combination of wing body and tail, both combined formulas. So we should here we need to consider the formulas for both combined only. So the combined formula, I will write the formula, just you try to solve the sum. Okay, so cm0 equal to cm ac WB, that is a CM about the aerodynamic center, plus BH into AT into I plus epsilon naught, or we can say this I as IT plus epsilon dot, say epsilon dot. So the values for epsilon dot and all, just take it from the last previous sum. Okay, so the previous sum epsilon dot is equal to 0. So the straight away you can use that epsilon dot equal to 0 here also, and IT the tail setting angle, and the previous sum also same. All here also I am using the same values only. So IT is 2.7, then CM ACWB, this is AC, so ACWB, that is equal to minus 0.032. Then VH also 0.334. AT is 0.1 degree. So straight away you can substitute the values. So for CMAC, that is a minus 0.032 plus 0.34 into 0.1 into for IT 2.7, so that is equal to 2 into 2.7. Please calculate the value for CM0. Tell me the answer, guys.
Sir, 0.06.
Yes, point
0,
0.06.
06.
So value here is, it is positive. So therefore the aircraft is in balanced condition only. Okay. So here we got the CM0 value is positive. Therefore the aircraft is in stable condition. So but one more thing we need to find, that is the slope, that is dou cm cg divided by dou alpha. For dou cm cg I will write the formulas: dou cm cg divided by dou alpha a equal to a into h minus hac wb minus bh into at divided by a into 1 minus dou epsilon divided by dou alpha, dou epsilon divided by dou alpha. Substitute the values and find the answer. Just substitution only, small type of substitutions only. Substitute it and find the answer. Guys, whether you are solving the sum,
Sir, minus 0.08.
minus 0 point.
0.8625.
Okay, fine. So the answer is negative only. So we know that if GM0 is positive and dou CMCG divided by dou alpha is negative, straight away we can say the aircraft is longitudinally static stability and balance. It is in it is longitudinally statically stabilized and balanced. Okay. So this is not the answer. We need to write like this only. Okay. So here the answer is the aircraft is statically stabilized and balanced. Okay. We can move on to this sum. So this is another one sum. A statically stable aircraft has a CL alpha equal to 5 degree, where alpha is measured in radians. The coefficient of moment of the aircraft about the coefficient of moment of the aircraft about the center of gravity is given as dou CMCG equal to 0.05 minus 4 alpha. The mean aerodynamic chord of the aircraft wing is 1 meter. So the mean aerodynamic chord is 1 meter. The location of the neutral point of the aircraft from the center of gravity. So we need to find the location of the neutral point from the center of gravity. Okay. So shall we find this sum? So we can find the sum. So they have given values for CL alpha, that is a lift curve slope, that is equal to 5. Then also they have given values for dou cm cg, that is equal to 0.05 minus 4 alpha, and they asked us to find the neutral point location from the center of gravity. Okay. So shall we find, that is they have asked us to find the static margin. So we need to Whether you can able to solve or I need to help. You guys need my help for solving this sum. Do you have anyone please reply? Do you have the formula for the static margin and the neutral point sum? Whether you guys note down that formula? Okay, I will write down the formula for static margin and all. See, we will see. You can see here also from. So this is the value for static margin. So they ask us to find the static margin, this value for the that problem. So here we have dou CMCG divided by dou alpha A equal to minus A into static margin. So straight away you can say it is a static margin, no problem. Okay. So here they have given values for, but the given data is CL alpha equal to 5. That is a lift curve slope A equal to 5. And dou CMCG equal to 0.05 minus 4 alpha. But here we have the formula is for dou CMCG, but only we only have the formula for CMCG. What we can do? What we can do? Anyone? Please give me any suggestion for this. Give me a suggestion for this sum, guys. It's a gate problem. So please try to solve this sum. Easy only. So from the question itself, we can easily find this sum. How to solve this sum? So they have given both values also. Just they ask us to find the final answer. Okay. See here, they have given on clue CMCG equal to 0.05 minus 4 alpha. So they have given the value for CMCG in terms of alpha. So while differentiating, we can get some values now, because we have the formula like this: dou CMCG divided by dou alpha only. So dou alpha equal to minus A into static margin. I am writing like the static margin as SCM. Okay. So this A value they have already given, but we need to find, if we can able to find the dou CMCG by dou alpha value, we can easily solve the answer. Okay, we can get the answer. But for in order to solve that, they have given on clue that like this CMCG. So by differentiating like this, so dou CMCG divided by dou in terms of alpha. So dou alpha, by using alpha, we are differentiating this, so that in this equation what it will become, this term, it doesn't have alpha term, so it will become 0. So that is equal to minus 4. So by substituting here, minus 4 equal to minus 5 into minus 5 into S M. Okay.
So 0.8
Ah,
answer.
so the SM static margin is equal to 0.8. So this is the answer. 0.8 is the answer. Okay. Okay. Move on to the next sum. So here they asked us to find the free elevator factor. That's another sum to find the free elevator factor. So consider the airplane. Its elevator hinge moment derivatives are dou CHE divided by dou alpha t equal to minus 0.008, and dou CHE divided by dou del E equal to minus 0.013. AT, this is A suffix T, sorry, okay, equal to 0.1. Then dou CLT divided by dou LE equal to del equal to 0.04. Find the value for free elevator factor. Find the value for free elevator factor. So we need to find the value for F. So we know the F formula from here. F equal to 1 minus 1 by AT into dou CLT divided by dou del E into CHE divided by dou alpha T divided by dou CHE divided by dou del E. Okay. So I will write the formula here so that we can easily solve it. Yes. F equal to 1 minus 1 by AT dou CLT divided by dou del E into dou CHE divided by dou alpha T dou CHE divided by dou del E. Now just we can see here AT they have given, so this term we know. Dou CLT here they have given the value for dou CLT, that also we know. Then dou CHE divided by dou alpha T, that is they have given here, and dou CHE divided by dou del E, that also they have given. Just substitute the value and find the answer. Substitute the value and find the answer for this. Guys, substitute the values and just find the answer.
1.25, sir.
1.25. No. So I have explained earlier that we discussed earlier that F should be less than unity.
Sir, 0.075.
0.075.
No, sorry, sir. 0.753.
Okay, 0.753. Just
Yes, sir.
okay. See, we have discussed earlier that the free elevator factor should be less than 1. It should be less than 1. So if your answer is less than 1 only, it is correct. Okay. Suppose in just by heard the conditions and also, because suppose they are asking the same sum, they ask us to find the free elevator factor, but suppose they will give for finding the they will give the values like this, and your answer is beyond this 1.21 means your answer is wrong only. Okay, it should be less than 1 only, then only the answer is correct. So the answer is F equal to 0.754. That is the correct answer. Okay, everyone got the same answer now?
Yes, sir.
Okay, fine. So see here, which one of the following statement is true? So here we have 4 options. One is wing dihedral reduces roll stability while low wing increases roll stability. Then second one, wing dihedral increases roll stability while low wing reduces roll stability. Wing dihedral as well as low wing reduces roll stability. Wing dihedral as well as low wing increases roll stability. Please read this, and I discussed this dihedral wing earlier. So try to come up with the answers. Try to come up with the answer. So there are two types of wings. Okay, one is a low wing. This is the low wing, and another one is dihedral wing. I will explain the concept once again. Okay, so for if an aircraft have low wing, it is the stability is roll stability is less for low wing, because during roll the aircraft may move to either if it is rolling towards a starboard side, or a starboard side means the side slip angle will be also in the same side, and the side slip will be act on this act towards the starboard side. And if it is rolling to port side means the side slip will act on that direction. If it is rolling to this direction means side slip will be in this direction. If it's rolling towards in opposite direction means side slip will be acting on this direction. So this configuration, the stability is less, the roll stability will be less. Roll stability is less for low wing configuration. So here low wing increases roll stability. This is wrong. Sorry, yes, this is wrong. And also here also low wing increases roll stability. This also it is wrong. But for a dihedral wing, the lift will be if it is rolling towards this side, one side the lift will be more, and another side the lift will be, here the lift will be more, and another side the lift is reducing. So what will happen when it is rolled? It will be regain its original position. So the roll stability is more in dihedral wing. So the answer will be here roll wing dihedral and low wing reduces roll stability. Wing dihedral increases roll stability. So this answer is also wrong. So the answer is wing dihedral increases roll stability while low wing reduces roll stability. So the answer is B. Okay. So the answer is B. So that's all. So this is the last problem. Here we have this figure below shows the variation of CM versus angle of attack for three combination. One is combination of elevator deflection. So we have seen the elevator reflection and location of center of gravity. In this figure, line P, Q and are parallel, and where Q and R are have the same intercept on CM axis. So if this type of diagram occurs, see here which of the following statement is true? Line P and Q corresponds to the same center of gravity. Line Q and R correspond to same center of gravity location. Line P and Q corresponds to the same elevator deflection. So here I can easily say elevator deflection means when the elevator is deflected, your lines will be moved to another location. So the elevator deflection is different for all three lines, that is P, Q and R lines. So this answer will be wrong, and this answer lies for this three options only. So the first line P and R correspond to the same center of gravity location. So we can see that if there is an intercept, the center of gravity also changes. So you have the um, moment cohesion diagrams will be like this only for elevator deflection. That means the center of gravity won't change, but the elevator angle only changes. So for different angles we can get different lines like this. So here the equations, like already we told that Q and R have same intercept, so it is intercepting, so this answer is also wrong. And P and R, it is not parallel to each other, so therefore this is also wrong. So the answer is line P and Q corresponds to the same center of gravity location. So we have for elevator deflections and all, the lines will be parallel only. And parallel lines shift us from one angle of attack to another angle of attack because there is a deflection in elevator angle. That's why the lines will be shifted forward. Okay, so the answer is P and line P and Q correspond to the same center of gravity location. So that's all for today. We can see the Dutch roll, rudder lock, weathercock effect, and the remaining things, aileron reversal and all in our next class. So these things for the lateral, and mostly they will ask questions from this, but one or two questions are from Dutch roll and all. So that we will see later. Today it is enough for our enough. So everyone, you can leave now. We can see the remaining things in our next class. Okay, thank you.
Thank you.
Okay.